Hi students, we are going to do a discussion of a sample question paper for your plus 2 CBSE board examination. First, let us go real quick through the layout of the question paper. You know all these things, there are 35 questions for you to answer. You have to answer all the questions, you don't have a choice in between the questions, but you do have some internal choice with some questions. So you have 5 sections. Section A consists of 18 MCQs, so that carries 1 mark each. Next section, section B, we have 7 questions. You have to write very short answers for that, which carries 2 marks each. Next section, we have 5 questions, 3 marks each. Section D, that is a case-based question. You have 2 case-based questions that carries 4 marks each. And finally, the section E, that consists of the long answers. You have to write long answers for 3 questions, which carries 5 marks each. Okay. So you have to write the answer for all questions, and you may have internal choices for some of the questions, but mandatorily you have to answer all the 35 questions, right? So you have a lot of time. There is no need to take any kind of tension. You have ample time to answer all the questions, because answering the MCQs, the first 18 MCQs can be covered within a very short span of time. Okay. So let us move on to the questions. We are starting with the section A, the MCQs. Let's take a look at the first question. It is to write the IUPAC name of the compound. There is a compound given which contains a double bond, and we have 2 halogens, bromine and chlorine. So we have a double bond here, and we have bromine and chlorine that is coming as a substance, and you have to write the IUPAC name of the compound. So what will be the IUPAC name of the compound? So let's see how many carbons are present in this compound. So we have 1, 2, 3 and 4 carbons that are present. So obviously our compound is butene, because it has a double bond. So if you compare between halogens and double bond, the double bond gets the priority. So our parent compound is butene. And where are the substituents coming? We have chlorine as a substituent in the first carbon, and bromine that is coming as a substituent in the second carbon. So we have to arrange the substituents alphabetically. That means, so the name of our compound is going to be our option A, that is 2-bromo 1-chlorobutene. That will be the IUPAC name of our compound. The second question, on oxidation with a mild oxidizing agent like bromine water, that is bromine bar H2O, the glucose molecule is oxidized to. That is a direct question. So we know the answer. Oxidation of glucose molecule with bromine water will give you gluconic acid as the oxidation product. So our correct option is option C, that is gluconic acid. The third question, identify the correct pathway to convert propanoic acid to ethyl amine. So we have to convert a carboxylic acid into an amine, and we have to go to 2 intermediate products. So we have to get 2 intermediates, that is X and Y. So we'll have to use 3 reagents. There are different options for 3 reagents that is given. So we have to choose the appropriate set of reagents by which we can convert a carboxylic acid into an amine in 3 steps. So let us see which is the best option that is available. Let us take a look at option B. The first reagent that we use is thionyl chloride. That means the acid will be converted into the corresponding acid chloride. And then when it reacts with the ammonia, that will be converted into the corresponding amide. That is, the acid chloride will be converted into the amide. And then when an amide reacts with the bromine water, that will be converted into the corresponding primary amine. So that is the best option that we have. So the set of reagents that we have to use will be option B. So first, the carboxylic acid is going to react with the SOCl2. So the reagent A is thionyl chloride. So we'll be getting the corresponding acid chloride, that is CH3, CH2, CO, Cl will be obtained as the product. And then we'll have to react this acid chloride with the ammonia. So that will give you the corresponding amide as the product. That is CH3, CH2, CONH2 will be obtained as the product. And the reaction of that amide with the bromine and KOH, that is Br2 and KOH, that will give you the corresponding primary amine as the required product. So our correct answer is option B. Question 4. Which of the following compounds will have the highest melting point? So we have to compare the melting points of this 4 substituted compounds of benzene. We have chlorobenzene, orthodichlorobenzene, metadichlorobenzene and paradichlorobenzene. So if you are looking for the melting point, we are looking for the arrangement of these compounds in the solid state. So if you compare between the ortho, meta and para isomers, we know that the para isomer is the most symmetric isomer. So para dichlorobenzene will have a structure like this. That means we have two chlorines present in the 1 and 4 position. So in the solid state, para dichlorobenzene will be the most symmetric product. So that will have the most symmetric arrangement. That means it will have the highest melting point among the 4 given compounds. So our correct option is option D, para dichlorobenzene. The fifth question. Aldehydes other than formaldehyde reacts with Grignard reagent to give addition products which on hydrolysis. That means we have been asked the reaction between an aldehyde and a Grignard reagent. So we have to know that reaction. When formaldehyde reacts with the Grignard reagent which has a general formula RMgX, the product that we obtain will be a primary alcohol. And when all the other aldehydes other than formaldehyde, that means RCHO, reacts with the same Grignard reagent, the product that we obtain will be secondary alcohols. And when ketones do react with the Grignard reagent, the product that we obtain will be tertiary alcohols. So our question is, when all other aldehydes other than formaldehyde reacts with Grignard reagent, the product that we obtain will be secondary alcohol. So this is a very important reaction. We have to know the reaction of Grignard reagent with aldehydes and ketones and the corresponding products that we obtain. So in this case, the product that we obtain will be a secondary alcohol. Sixth question. The oxidation of toluene to benzaldehyde by chromyl chloride, it is called as. It's a very direct question. That is a named reaction. So we'll have to know the reaction and the reagents that we use. So here, toluene is oxidized to benzaldehyde and the reagent that we use here is chromyl chloride. So we know the reaction, the name reaction, it is called as Itard reaction. That is our correct option, option A. The seventh question. Phenol is less acidic than, we have 4 options here. We have ethanol, orthonitrophenol, orthomethylphenol and orthomethoxyphenol. So we have to compare the acidity of these 4 compounds with the acidity of phenol. So let's see here, we have a nitro group substitution in phenol. That means this is an electron withdrawing group. And we have methyl group, that is an electron donating group, and we have orthomethoxyphenol. The methoxy group is also an electron donating group. So whenever there is an electron withdrawing group that is present, so that will decrease the acidity of phenol. That means orthonitrophenol will be less acidic than phenol. So our correct option will be option B, that is orthonitrophenol. The 8th question. Which of the following alcohols reacts most readily with Lucas reagent? So Lucas reagent is a test to identify the type of alcohol that we have in our hand. So which is the alcohol that is going to react most readily with Lucas reagent? We know that tertiary alcohol is going to readily react with Lucas reagent. So we have to look for any tertiary alcohol that is present. So if we look at the options, we can see that we have a tertiary alcohol that is present here, that is option C. So option C will be our correct answer. This tertiary alcohol is going to react most readily with the Lucas reagent. The 9th question. Which of the following compound is formed when benzyl alcohol is oxidized with KMnO4? We are going to oxidize an alcohol, benzyl alcohol with KMnO4, and what will be the product that we obtain? Are we going to get carbon and water or benzoic acid or an aldehyde or a ketone? So we know that KMnO4 is a very strong oxidizing agent. So that is going to readily oxidize the alcohol directly into a carboxylic acid, COH. So we will be obtaining the corresponding carboxylic acid, that is benzoic acid, will be obtained as the product because the oxidizing agent that we use is a very strong oxidizing agent. So our correct option is option B, that is benzoic acid. The 10th question. The boiling point of an azeotropic mixture of water and ethanol is less than that of pure water and pure ethanol. So what will be the type of deviation that is shown by the mixture, whether it is going to show a positive or negative deviation or whether it is not going to show any deviation at all? So here we have an azeotropic mixture of water and ethanol. The boiling point of that mixture is found to be less than that of pure water and that of pure ethanol. So what will be the type of deviation that will be shown? We have the boiling point of the mixture that is less than that of the pure component, right? So the type of deviation that is shown will be positive deviation from the Rolle's law. So a mixture of water and ethanol, that is going to show a positive deviation from Rolle's law. That is because the interaction between the water molecules and ethanol molecule is lesser than the type of interaction that is happening between pure water molecules and pure ethanol molecules. So the type of deviation that is shown there will be positive deviation from the ideal behavior. So the correct option is option B, that is positive deviation. The 11th question. For a reaction X plus Y giving Z, that is a question from kinetics, the rate of the reaction is directly proportional to the concentration of the reactant X. So we have been asked what is the molecularity and order of the reaction. We have to find the order and molecularity of the reactions. This is a simple reaction X plus Y giving Z. So how do you find the molecularity of the reaction? That is the number of reactants that is participating in the reaction. So we have X and Y that is reacting together to give you the product. So the molecularity of the reaction is 2. And the rate of the reaction is directly proportional to the concentration of the reactant that is raised to the power 1. So the rate of the reaction depends only on the concentration of one of the component, that too is directly proportional. So that means the order of the reaction is 1. So we have the molecularity of the reaction 2 and order of the reaction is obtained as 1. So our correct option is option A, which says that the molecularity is 2 and order of the reaction is 1. So that is our correct answer. The 12th question. Which of the following 0.1 molar aqueous solution will have the lowest freezing point? So this question is from colligative properties. So depression in freezing point is one of the colligative properties. So that depends upon the number of particles. As the number of particles increases, the depression in freezing point, that is the colligative properties value, also increases. So let us see how these compounds are going to dissociate. The first one is a sucrose molecule. So that will dissociate to give you 2 monosaccharide units, that is glucose and fructose. So we will have C6H12O6, 2 molecules. So here the value of Van der factor I will be equal to 2. And similarly, if you take potassium iodide, that is going to dissociate into the corresponding ions K plus and I minus. So there also the value of Van der factor is going to be 2. So we will have 2 ions obtained from one single molecule. And what is C2H10O5? This is actually a trihydrate of acetic acid. So this molecular formula can be written as CH3COOH dot 3H2O. So we know that acetic acid is a molecule that is going to undergo association and not dissociation, right? So that means the number of molecules is going to be lesser than the amount of molecule that we have taken. So obviously that is not going to be the answer. And what about the case of aluminium sulfate? Aluminium sulfate is going to dissociate into 2 aluminium 3 plus ions and 3 sulfate ions. So we'll have a total of 5 particles, 5 number of particles that is obtained from a single molecule. The value of Van der factor is going to be highest for aluminium sulfate. So as the number of particles is higher, the observed colligative property will be higher in the case of aluminium sulfate, which means this molecule, aluminium sulfate, is going to have the lowest freezing point because our colligative property is depression in freezing point. That depression will be maximum in the case of aluminium sulfate because the number of particles is greater in the case of aluminium sulfate. So that is going to be our correct option, option A, aluminium sulfate. The 13th question. Of the following reaction, which is used to make a fuel cell? So very simple question, direct answer. So you don't even have to look at the other options. If you take a look at option C, that is 2H2 plus O2 gives 2H2O. That is the equation for the hydrogen-oxygen fuel cell. That is the net reaction that is happening in a hydrogen-oxygen fuel cell. Hydrogen gas and oxygen gas are combined to give you water as the product. So the combustion energy is being converted into electrical energy, and that energy is being used. So our correct option is option C. The 14th question. Half-life period of a zero-order reaction. What is the half-life period of a zero-order reaction? That is also a very direct question from our text. Okay, so in the case of a zero-order reaction, what will be the half-life? The half-life of the reaction will be R0 divided by 2K. That will be directly proportional to the initial concentration of the reactant that we have taken. So in the case of a zero-order reaction, the half-life of the reaction will be R0 divided by 2K. So our correct option is option D. Now we are moving to the next type of questions, that is the assertion reason question. So here you will have two statements. We will have an assertion statement and a reason statement, and we will have four options given, and you have to select the correct option accordingly. So if you want to choose option A as the answer, then both assertion and reason have to be true, and the reason statement has to be the correct explanation for the assertion statement. And if you have to select option B, both assertion and reason statement has to be true, but the reason statement will not be the correct explanation for the first assertion statement. And if it is option C, the assertion statement should be true, but the reason statement should be false. And if the last option D, assertion should be false, but the reason statement should be true. So now let us take a look at the questions. 15th question. The assertion statement, that is Fe(CN6) 3- is weakly paramagnetic, whereas Fe(CN6) 4- is diamagnetic. And we have a reason statement, Fe(CN6) 3- has a +3 oxidation state, whereas Fe(CN6) 4- has a +2 oxidation state. So let us look at the reason statement first, because it says about the oxidation state. If you take Fe(CN6) 3-, the total charge of CN6 will be 6-, and the total charge of the complex is 3-. So obviously Fe3+ has to be in the +3 oxidation state. And if you take Fe(CN6) 4-, do the same method, we see that the iron is in the +2 oxidation state. So the reason statement is correct. So we have to take a look at the electronic configuration of Fe3+ and Fe2+. We know that the atomic number of iron is 26, so the configuration is going to be 4s2 3d6. And if you take Fe3+, the electronic configuration is going to be 3d5. 4s0 3d5 in the case of Fe3+, and in the case of Fe2+, the electronic configuration is going to be 4s0 and 3d6. So now the assertion statement says that Fe(CN6) 3- is weakly paramagnetic, whereas 4- is diamagnetic. So we'll have to look for the presence of unpaired electrons in this compound. So we know that cyanide is a strong ligand, and that is going to cause the pairing of electrons. Now if you take Fe3+, the first compound, we have 5 electrons in the d orbital. So there is going to be 1 electron that is unpaired, and the 4 electrons are going to be paired. Whereas in the case of D6 configuration, all the 6 electrons are going to be paired. That means there will be a total of 3 pairs. So Fe(CN6) 4- that do not have any unpaired electrons, so that is going to be diamagnetic. That is correct. And the first compound, that is weakly paramagnetic because it has 1 unpaired electron that is present. Okay. So the assertion statement is also true, and the reason statement is also true. But is it the correct explanation? That is not entirely the correct explanation. Now, the reason because that became paramagnetic and diamagnetic is because the ligand that came in, cyanide- is a strong ligand. So it has nothing directly to do with the oxidation state of the central metal atom. So we cannot entirely say that the reason statement is the correct explanation for the assertion statement, but all the individual statements are true. So which is the option that we have to select? We'll have to select option B, that is both the assertion and reason statements are true, but the reason is not the correct explanation for the assertion statement. Now the next question. The assertion statement is aryl halides undergo nucleophilic substitution reaction with ease. And the recent statement says that the carbon halogen bond in aryl halides has a partial double bond character. So we know that that statement is true. The carbon halogen bond, if you take an aryl halide, the carbon halogen bond that is present, that will be having a partial double bond character due to the resonance that is happening. So the recent statement is true. And the assertion statement says that aryl halides undergo nucleophilic substitution reaction with these. That is not a correct statement because the benzene ring is already an electron-rich species and there is no way that a nucleophile, a negatively charged species, is going to come and undergo a reaction in this electron-rich environment. So it is difficult for aryl halides to undergo nucleophilic substitution reaction. So the assertion statement is false and the recent statement is true. So we'll have to choose our options accordingly. The 17th question. Here the assertion statement is that the order of the reaction can be 0 or it can be fractional. So we know that that statement is true. The assertion statement is true. And the recent statement says that we cannot determine order from balanced chemical equation. That means the order of the reaction cannot be determined from the balanced chemical equation. That is also a true statement because the order of the reaction is an experimentally determined quantity. Okay. So both the assertion statement and the recent statements are true. And also the reason is the correct explanation for the assertion statement. So we'll have to choose the options accordingly. Now we can move on to the next question. The 18th question. So take a look at the assertion statement. It says that acetanilide is less basic than aniline. And the recent statement, acetylation of aniline results in the decrease of electron density on nitrogen. So first we have to compare the basicity of aniline and acetanilide. So that statement is true. We know that acetanilide is going to be less basic than aniline. And what is the reason for that? That is because the acetylation reaction of aniline, that will result in a decrease of the electron density on the nitrogen atom that is present as a substituent in the benzene ring. So both the assertion and the recent statements are true and the recent statement is the correct explanation for the assertion. So that means our correct option is going to be option A. That is going to be our correct answer. So we have answered all the 18 questions in the MCQ sections and now we can move on to section B. So in this section we will have to answer 2 mark questions. So we are starting off with the numerical problem. So let us see how we are going to solve it. The 19th question. The Henry's law constant for carbon dioxide and water is 1.67 into 10 raised to 8 pascals. So we have to calculate the quantity of carbon dioxide in 500 ml of soda water when packed under 2.5 atm pressure at 298 Kelvin. Right. So in the first class itself, we can know that the question is related with the Henry's law and we have to calculate the amount of carbon dioxide, that is the weight of carbon dioxide or the amount of carbon dioxide that is present in a particular volume of the solution. Right. So we can start off with the equation of Henry's law, which states that the partial pressure of the component is going to be proportional to the mole fraction of the same component, in this case that is carbon dioxide, which is going to be present in the solution. So that is where the Henry's constant Kh comes in. So the value of Henry's constant is given, that is 1.67 into 10 raised to 8. That is given in pascals, but the pressure in which the dissolution of carbon dioxide is done, that is given in atm. So we'll have to convert this atm into pascals. For that we'll have to multiply this with 1.01 into 10 raised to 5. So we'll have to do 2.5 into 1.01 into 10 raised to 5. So if we take 0.1 of 2.5, that is going to be 0.025. So our total value will be 2.525 into 10 raised to 5 pascals. So that is the value of 2.5 atm converted into pascals. So we can substitute these values in the equation. So we have the value of Henry's constant and the pressure, that is 2.525 into 10 raised to 5. That is going to be equal to the value of Henry's law constant 1.67 into 10 raised to 8 into the mole fraction of carbon dioxide. So from this equation, we will be getting the mole fraction of carbon dioxide. So if we know the mole fraction, from that we can calculate the number of moles, and if we multiply it with the corresponding molecular mass of carbon dioxide, we will be getting the amount of carbon dioxide or the weight of carbon dioxide that is going to present. So the steps are going to be easy. We only have to concentrate on the numerical simplifications. So we can calculate the mole fraction of carbon dioxide as 2.525 into 10 raised to 5 divided by 1.67 into 10 raised to 8. So our answer is going to be, so we have 10 raised to 5 and 10 raised to 8. So that will give you 10 raised to minus 3. And we have 2.525 and 1.67. And that value will be approximately equal to 1.5. Right, so 2.525 is roughly going to be 1.5 times that of 1.67. So we'll have our answer as 1.5 into 10 raised to minus 3. That is going to be the mole fraction of carbon dioxide. So I got the mole fraction of carbon dioxide to be 1.5 into 10 raised to minus 3. So we'll just take a note of that here. We have the mole fraction of carbon dioxide is 1.5 into 10 raised to minus 3. Now we have to just substitute this value in the equation for the mole fraction of carbon dioxide. So we know that the mole fraction of carbon dioxide, that is going to be the number of moles of carbon dioxide divided by the total number of moles in the solution. That means the number of moles of carbon dioxide plus number of moles of water. Right? So we have to find out the number of moles of water. Here it is 500 ml of soda water that is present. So the weight of the water will be 500 gram. So how will you calculate the number of moles of water? So we have the number of moles of water that will be equal to mass in gram, that is 500, divided by the molecular mass, that is 18. So that is going to be 250 divided by 9. So what will be the value of 250 divided by 9? 763. So that is going to be 27.7. Right. Approximately 27.7. Okay. So we have the number of moles of water obtained as 27.7 moles. So we have to calculate the number of moles of carbon dioxide. So in the denominator, as this is going to be a small value, we can ignore that value. So number of moles of carbon dioxide divided by number of moles of water, that is equal to 1.5 into 10 raised to minus 3. That means number of moles of carbon dioxide divided by 27.7, that is going to be 1.5 into 10 raised to minus 3. So from there we can calculate the number of moles of carbon dioxide, that is going to be 1.5 into 10 raised to minus 3 into 27.7. Right. 27.7 into 1.5. So we can roughly do 28 into 15. So that is going to be approximately 420. Okay. 420 into 10 raised to minus 3. Moles. Okay. So that is the number of moles of carbon dioxide. So now we have obtained the number of moles of carbon dioxide, and if we want to find the amount of carbon dioxide or the weight of carbon dioxide, what we can do that we can multiply this 420 into 10 raised to minus 3 with the molecular weight of carbon dioxide, that is 44 gram per mole. Okay. So we'll have 420 into 44 into 10 raised to minus 3. So we'll have to do 42 into 44 multiply with the 10. That means 42 into 44 into 10 raised to minus 2. So that will give you the answer approximately as 1.848. And what is the unit? We are finding the weight of carbon dioxide. That means the weight of carbon dioxide is equal to the number of moles of carbon dioxide multiplied by the molecular mass of carbon dioxide. So our final answer will be, after the simplification, the answer will be 1.848 grams. So that is the amount of carbon dioxide that is present in the given solution, right? So our final answer is going to be, that means the quantity of carbon dioxide in 500 ml of soda water when packed under this given pressure, that is going to be 1.848 grams. So that is our final answer. Now the next question, the 20th question. How would you obtain a given compound from a given starting material? The first question is, how do you prepare picric acid, that is 2,4,6-trinitrophenol from phenol? And secondly, how do you prepare 2-methyl-propene from 2-methyl-propanol? So we have an or question. So this question is going to have an internal question. So you can either answer this set of questions or the next set of questions. So first let us see the answer for these two questions. How do you prepare picric acid from phenol? So starting from phenol, we just have to do the nitration reaction. So if we do a nitration reaction with the concentrated nitric acid on phenol, we'll have an NO2 group that is being substituted at the 2 ortho positions and 1 para position. So we'll be obtaining 2,4,6-trinitrophenol, that is picric acid, as the product. So the nitration of phenol will give you picric acid as the product. And the next question is to prepare 2-methyl-propene from 2-methyl-propanol. So we'll have to start with 2-methyl-propanol. So starting with an alcohol, we'll have to prepare an alkene. So that can be done by the acidic dehydration reaction. That means if you react an alcohol with concentrated sulfuric acid, there will be an elimination of a water molecule and we will be obtaining the corresponding alkene as the product. So we have to start with the 2-methyl-propanol. So we'll be starting with the propanol. We have a methyl group that is present at the second carbon, right? So we have CH3, CH, CH2, OH. Okay. So this is 2-methyl-propanol, and if you react this compound with the concentrated sulfuric acid, a dehydration reaction is going to happen. That means OH will be lost from this carbon, from the alpha carbon, and a hydrogen will be taken from the beta carbon, and a double bond will be formed here. That means we will be obtaining CH3, CH, CH3, double bond CH2. This hydrogen is not going to be here. See, double bond. So we have obtained the required product. Okay. So this is the answer for the two preparations that have been asked in our question. And we also have an OR question here. So you can either answer the first two set of questions or you can answer these two questions. So here also we have two sub-questions. The first one is to arrange the following three compounds. We have paracresol, para-nitrophenol and phenol. We have to arrange the following compounds in the increasing order of their acid strength. That means we will have to compare the acidic strength of phenol when an electron withdrawing group and an electron donating group is going to come as a substituent in the ring. And the B question, how can we obtain alcohols corresponding to Markovnikov and anti-Markovnikov rule from alkenes? So we'll have to prepare alcohols from alkenes, and which reagents do we have to use in order to obtain a Markovnikov product and an anti-Markovnikov product? So let us answer these questions. They are very easy questions. All of them are direct questions. Alright. So the first case we only have to remember is that when an electron donating group or electron withdrawing group is coming as a substituent as phenol, how is it going to affect the acidity of phenol? So the presence of an electron withdrawing group, that will increase the acidic strength of phenol. So whenever we have an NO2 group that is coming, that will be increasing the acidic strength of phenol, and the presence of an electron donating group, that will decrease the acidic strength of phenol. So we'll have to compare the acidic strength of phenol, that is C6H5OH, with the acidic strength of paracresol and para-nitrophenol, right? So cresol is going to be CH3. So this is our para-cresol and this is our para-nitrophenol. Right. So our condition is that the presence of an electron withdrawing group, that is the presence of NO2 group, that is going to increase the acidity of phenol, and the presence of an electron donating group, that is methyl group, that will decrease the acidic strength of phenol. So if you compare the acidity of these three compounds, we can see that the one with the methyl group, that will be having the least acidic strength. That means this one is going to be the least acidic. That means the para-cresol compound is going to be the least acidic, and then comes phenol, and the most acidic will be para-nitrophenol because of the presence of an electron withdrawing group that is present. So this is the correct increasing order of acidity for the given compounds. Now the next question that is asked is that how would you obtain alcohols corresponding to Markovnikov and anti-Markovnikov products starting from alkenes? So that is a direct question which has been neatly explained in the preparation of alcohols, right? So if you start from alkenes and if you do an acid catalyzed hydration, we will be obtaining the corresponding Markovnikov product. That means the OH minus is going to attach to the most substituted carbon. And if you want an anti-Markovnikov product, we will have to do hydroboration oxidation. That means we will be obtaining the anti-Markovnikov product. That means if you start with the CH3, CH double bond, CH2. Now, if you do an acid catalyzed hydration, we will be obtaining the Markovnikov product. That means the OH is going to attach here at the most substituted carbon and the hydrogen is going to be attached here, right? So this is the corresponding Markovnikov product that is obtained through acid catalyzed hydration. Whereas if you do hydroboration oxidation, on the other hand, we will be obtaining the anti-Markovnikov product. That means the OH is going to be attached here. That means here the product is going to be CH3, CH2, CH2, OH. Right. So this is how we obtain Markovnikov and anti-Markovnikov product using suitable reagents starting from alkenes. Now the next question, the 21st question. How would you account for the following? The first statement, having the same configuration, Cr2 plus is reducing in nature whereas Mn3 plus is oxidizing in nature. And the next statement, in a transition series of metals, the metal which exhibits the greatest number of oxidation state occurs in the middle of the series. So let us look at that statement first. In the transition series of metals, though, the property of transition metals is that it shows variable oxidation state, and the metal which shows the highest number of oxidation state will be occurring in the middle of the series. So the element that is occurring in the middle of the series, that means if you consider the 3D series, that will be manganese, which has a 3D5 configuration. So that configuration will be having the largest number of unpaired electrons that is present. So that will be responsible for the most number of oxidation state that is exhibited by the element that is present in the middle of any transition metal series, because that has the largest number of unpaired electrons, which gives the element the ability to show the most number of oxidation states. Now the first statement, we have to compare the nature of Cr2 plus and Mn3 plus. So both Cr2 plus and Mn3 plus has the same configuration. So what is the configuration of manganese 3 plus? So if you take manganese 3 plus, if you take manganese, that has a D5 configuration, and if you take manganese 3 plus, it will be having a D4 configuration, and Cr2 plus is also having a 3D4 configuration. So having the exact same configuration, Cr2 plus is going to be reducing in nature, whereas Mn3 plus is going to be oxidizing in nature. Correct. So if you take Mn3 plus first, it will be having a D4 configuration. So it is said that Mn3 plus is oxidizing in nature. So if Mn3 plus is oxidizing, this Mn3 plus will have to undergo reduction. That means it will be gaining an electron. That means the D4 configuration will be converted into D5 configuration. So since the half-filled d orbital configuration has an extra stability, that will explain the oxidizing nature of Mn3 plus. That is going to get reduced by accepting an electron and become Mn2 plus. Whereas if you take Cr3 plus, that is going to be Cr2 plus, that is going to be reducing in nature. That means Cr2 plus is going to get oxidized into Cr3 plus. So there we will have to go for the crystal field theory explanation. So we'll have the set of orbitals that is going to be split into the T2g and the Eg set of orbitals. So in that case, we'll have a D4 configuration, and if it is getting oxidized, that will be converted into D3 configuration. So if Cr2 plus attains the D3 configuration, that will be having a partially filled T2g set of orbitals that is going to give an extra stability. So that is why Cr2 plus is going to be reducing in nature, because it is going to get oxidized, that is going to lose one of the electrons, and that will be converted into Cr3 plus. So Cr3 plus will be having a 3D3 configuration which has a partially filled T2g set of orbitals. So this is how we explain the oxidizing nature of Mn3 plus and the reducing nature of Cr2 plus when both of them are having the same D4, 3D4 electronic configuration. Now the next question. This is a direct question. We have to write the reactions or equations that is involved with the following reactions. The first one is a Reimer-Tiemann reaction, and the second one is Kolb's reaction or Kolb's electrolytic reaction. Both of the reactions are neatly mentioned in our textbook. This is a very direct question. So what is Reimer-Tiemann reaction? The first reaction, that is where we prepare salicylaldehyde starting from phenol. So first we will have to react phenol with the chloroform in aqueous sodium hydroxide. So that is going to give you a corresponding intermediate and the corresponding sodium cation substituted product. And when we do an acid catalyzed hydration, that will give you the corresponding aldehyde, that is salicylaldehyde is the product. So Reimer-Tiemann reaction is how we prepare salicylaldehyde from phenol. So that is a very important name reaction. And what about the second reaction? That is Kolb's electrolytic reaction. So that is where we prepare a hydrocarbon or an alkane starting from the salt of a carboxylic acid. So the alkane that we obtain, that will have double the number of carbon atoms that is present in the alkyl group of the carboxylic acid that we are taking. So here we have started the reaction with the sodium salt of acetic acid. So that alkyl part is going to contain one carbon atom. That means the product that we obtain will be having two carbon atoms. That means the product that we obtain will be ethane. So this reaction, that is an electrolytic reaction, and that is going to move forward through a free radical mechanism. So at the anode, the oxidation reaction is going to take place where the CH3CO minus ion, the acetate ion, will lose 2 electrons and will be obtaining 2 methyl radicals, and carbon dioxide gas will be emitted at the anode. And these 2 methyl radicals are combined together to give you the hydrocarbon ethane as the product. So that will be obtained at the anode and carbon dioxide gas will be liberated. And a reduction reaction will be happening at the cathode where hydrogen gas is going to be liberated. So here a water molecule is going to get converted into OH minus ion and a hydrogen free radical. 2 hydrogen free radicals will combine together to give you hydrogen gas. So the corresponding hydrocarbon and carbon dioxide gas are obtained at the anode and hydrogen gas is liberated at the cathode. So this is the Kolb's electrolytic reaction where we obtain a saturated hydrocarbon as a product starting from the sodium salt of a salt of a carboxylic acid, and the hydrocarbon that we obtain will be having double the number of carbon atoms that is present in the alkyl group of the starting material or the starting carboxylic acid that we have taken. So both of them are 2 important named reactions. So we'll have to remember both of them. The next question, 23rd question. Explain what is meant by a peptide linkage and a glycosidic linkage. Here also we can see that there is an internal choice. So we can either answer these 2 set of questions or you can go for the next set of questions. So this is the direct question. What is a peptide linkage and what is a glycosidic linkage? A peptide linkage is something that is happening in the case of polypeptides or proteins, and a glycosidic linkage is happening in the case of polysaccharides or disaccharides, right? So let us see the linkage. So if we take the glycosidic linkage, so that is a linkage that is happening via an oxygen atom where two monosaccharide units are combined together to form a disaccharide unit. In the case of peptide bond, that is obtained by the reaction between or the condensation between a carboxylic acid group in one amino acid and the NH2 group in another molecule of amino acid. So molecule of water will be eliminated from here, and there is a corresponding amide linkage, CONH linkage, that is formed, which is going to bind together the two amino acids that we have taken. So this is called a peptide linkage, okay, which is the CONH bond that is happening in the case of polypeptides or proteins. Okay. So these are the two important types of linkages that is happening. The first one, glycosidic linkage, is happening in the case of polysaccharides, and the second one, peptide linkage, is happening in the case of polypeptides or proteins. So that was our one set of questions, or we can answer the next set of questions. We have two questions here. The first question is that sucrose is also called an invert sugar. Why? And the next question, give any reaction of glucose which cannot be explained by the open chain structure of glucose molecule. So the first question corresponds to the optical activity of the sucrose molecule. So if you hydrolyze sucrose, we will be obtaining one molecule of glucose and one molecule of fructose. Correct? So sucrose is actually a dextrorotatory molecule. Sucrose is dextrorotatory, and if you consider glucose and fructose, you can see that fructose is levorotatory and glucose is dextrorotatory. But the value of optical rotation is more in the case of fructose than in the case of glucose. So after hydrolysis, we can see that there is a change in the optical activity, in the change in the optical rotation of the resultant solution. So that is why sucrose is called as an invert sugar. What about the next question? Give any reaction of glucose which cannot be explained by the open chain structure. That is a simple question. So if you consider the Schiff's test, that means the reaction of aldehydes with Schiff's reagent, we will be obtaining a deep violet red color as the observation of the reaction. If a free CHO group or an aldehyde group is present, that will give a positive Schiff test. But here glucose will not give you the Schiff's test. That means the free aldehyde group is absent in the case of glucose molecule. That means if we consider the open chain structure, that cannot explain why glucose does not give the positive Schiff's test. That is because there has a semi-acetal structure where the CHO group is not readily available for reaction. So that is one reaction which cannot be explained by the open chain structure of glucose molecule. There is also the sodium bisulfate test, that is NaHSO3 test, which also cannot be explained by the open chain structure because the free CHO group is not present there. Okay. Now the next question, 24th question. Complete the following reactions. We have two reactions. We'll have to write the products for that reaction. The first reaction, we will be starting with a diazonium salt, right, because we have C6H5N2Cl. Right. And the reaction of that diazonium chloride with the H3PO2, that is hypophosphorus acid and water. We'll have to write the products for that reaction. And the second reaction, that is the reaction of C6H5NH2 aniline with the bromine water. So what are the products that we obtain here? Here it will be the bromination of aniline that is taking place, correct? And what will be the products of the first reaction? The products of a diazonium salt reacting with the hypophosphorus acid. So we have the reactions that is written here. We are starting with an aryl diazonium chloride and the reaction of that with the hypophosphorus acid and water. That will give you the corresponding hydrocarbon, the corresponding aromatic hydrocarbon as the product, and the byproducts will be nitrogen gas and H3PO3, that is phosphorus acid. Phosphorus acid and HCl will be obtained as the product. So this is a direct reaction where the diazonium salt is converted into the corresponding hydrocarbon and nitrogen gas is being eliminated. And what about the second reaction? the reaction of aniline with bromine water. So there the reaction will be the bromination that is happening. So we cannot control whether the bromination is happening in the ortho or para position. So we will be obtaining substitutions at both the ortho positions and one para position, and the product will be 2,4,6 tribromoaniline. That is the product that we obtain as a result of bromination. Okay. So these are the corresponding reactions we have been asked to write. Now the next question, 25th question. State the reasons for the following. The first statement, pKb value for aniline is more than that of methylamine. And the second statement, primary amines have a high boiling point than tertiary amines. Okay. So what's the first statement? The pKb value for aniline is more than that of methylamine. So we know that greater the pKb value, lesser the basicity. Right. So the statement says that pKb value for aniline is more. So aniline has a greater pKb value and methylamine has a lesser pKb value, which means that methylamine is more basic than aniline. So why is methylamine being more basic than aniline? So if you take methylamine, we can see that there is a presence of methyl group. The inductive effect of methyl group, the plus I effect of methyl group will make the donation of lone pair of nitrogen easier, making it more basic. Whereas in the case of aniline, instead of a methyl group, there is a benzene ring that is present. So the lone pair of nitrogen in this case will be less available because it will be in resonance with the benzene ring that is present. So if you compare methylamine and aniline will be less basic than methylamine. So that explains why the pKb value of aniline is more than that of methylamine. Okay. And the second statement, primary amines have higher boiling points than tertiary amines. Obviously, because there is hydrogen bonding that is happening in the case of primary amines, because we have two hydrogen atoms of one molecule that will be in hydrogen bonding with the nitrogen atom of another amine molecule. But that hydrogen bonding is not possible in the case of tertiary amines because there are no hydrogen atoms present in tertiary amines for hydrogen bonding. So the higher boiling point will be in the case of primary amines than that of tertiary amines. So that will be the explanation for the two statements that is given here. Right. So we have answered the questions in section B, which are all 2-mark questions. So now we can move on to section C. There we'll have 3-mark questions to answer. The first one is a numerical question. So let us read the question. At 300 Kelvin, 36 gram of glucose present in a liter of its solution has an osmotic pressure of 4.98 bar. So this is a question related with the colligative property, osmotic pressure. Now if the osmotic pressure of the solution is 1.52 bars at the same temperature, what would be its concentration? Here we'll have to find the concentration of a solution given the osmotic pressure at two different values. So we have a value of osmotic pressure, that is pi, that is given in the first condition as 4.98 bar. So what is the equation for osmotic pressure? That is given as pi is equal to CRT, where concentration is given as the number of moles of solute present per liter of the solution, which in this case is same as the molarity multiplied by R into T and by V into RT. So it is given that at 300 Kelvin, so the temperature is going to be constant here, that is not going to change. R is a constant and the volume of the solution is also taken as a constant. So let's take at the first condition. 36 gram of glucose present in a liter of its solution has an osmotic pressure of 4.98 bar. Right. So in the first case, if you consider the first solution, the osmotic pressure is 4.98 bar. So that is equal to, here it is given that there is 36 gram glucose is present. So what is the equation for number of moles? The number of moles N is given as the weight divided by the molecular mass. Weight of the substance divided by the molecular mass. So since it is glucose, the molecular weight is going to be 180. So we can write N as weight of the glucose, that is 36 divided by 180 into 1 by V into R into T. We can cut it directly. This is 1 and 5, right? Now in the case of second solution, the osmotic pressure is given as 1.52 bars. The osmotic pressure is 1.52 bars and we have to find the concentration. We'll have to find the concentration of that solution. Alright. So that is again N by V into R into T. Right. So we have two equations here. So we'll have to find the concentration term that is present. Right. So if you compare both the equations, we can see that there are three terms that is constant. Temperature is going to be constant, R is already a constant, and the volume is also going to be a constant. Right. So we'll have to compare only the remaining terms. Okay. So now if you could divide these two equations, we can easily obtain the value of the N by V term or the concentration term that is present. Right. So now I'm going to divide the second equation by the first equation. That means 1.52 is equal to the concentration that we require. And now I'm going to divide that by the first equation, that is 4.98 divided by 1 by 5. Right. So that will give you 5C. Right. So from this we can easily find the value of concentration, that is 1.52 divided by 4.98 into 5. That will give you the required concentration of the glucose that is present. So this will be approximately 150 divided by 500 into 5. Sorry, divided by 5. So what will be the answer that we obtain? This will be approximately 3 by 50. That is roughly going to be equal to 0.06 molar. Right. So that is the concentration of glucose that is present in the second solution, which is at a pressure of 1.52 bar. So we should write the answer as the concentration of glucose. It means the concentration of glucose at 1.52 bar will be equal to approximately equal to 0.06 molar. So that will be the molarity of the second solution, which is at a pressure of 1.52 bars. Now let's move on to the 27th question. Predict the order of reactivity of the following compounds in SN1 reaction. So we have 4 compounds that is listed here. So we have to find the order of reactivity of these compounds towards the nucleophilic substitution unimolecular mechanism, that is SN1 mechanism. So we know that the SN1 mechanism follows through the formation of carbocation. The more stable the carbocation that is formed, the more inclined the compound will be to follow the SN1 mechanism. So let us see how substituted each of these compounds are. So if you take the carbon that is present in the first compound, you can see that there is only one substitution, only one phenyl group that is present in this compound. The rest 2 are hydrogens. Now in the second compound, you can see there is only a carbon atom that is present and the 3 of them are substituent group. We have 2 C6H5 groups and 1 methyl group that is present as substituents on the carbon into which the halogen bromine is attached. Now look at the third compound, we have 1 hydrogen and we have 2 phenyl groups as substituents. And in the last compound, you can see there is 1 C6H5 group and 1 methyl group. Those are present as the substituents. So the more substituted the compound, the more stabilized the carbocation will be, and that will be more inclined towards the SN1 mechanism. So you can follow either the ascending or descending order. So here I am following the descending order. Let us see. So the most reactive compound towards the SN1 mechanism will be, we could number the compounds as 1, 2, 3 and 4. The most substituted one among them is the second compound. So that will be more inclined towards the SN1 mechanism. So I'm going to write here the second compound, which will be the most reactive or most favorable towards SN1 reaction. And then if you take a look at the third compound, you can see there are 2 phenyl groups which are present as the substituents. Right? So that should be the next compound, the third compound, which has 2 phenyl groups as a substituent. Now the fourth compound that has 1 phenyl group and 1 methyl group as a substituent, which is a slightly less reactive towards SN1 mechanism. So our next compound will be the fourth compound, and the least substituted compound among the 4 compounds that is given, the first compound, that will be the least reactive towards SN1 mechanism. So we have explained this order based on the stability of the carbocation that is formed. And we also have a B part for that question. So this is a series of reaction. We have to predict the products that is formed. Write the structural formula of the products A, B, C and D that is formed in the following sequence of reaction. So we're going to start with an alkyl halide, and the first reaction is with alcoholic KOH. So that is a strong base. So what is the reaction that is going to happen here? The elimination of a small molecule of HCl, that is dehydrohalogenation reaction, is going to occur, and the product that we obtain will be an alkene. So in the first reaction, the product that we obtain A will be after the elimination of HCl molecule. So our product will be CH3, CH double bond CH2. That means propene will be the product that is obtained in the first step. And the next reaction is the reaction with the HBr in the presence of peroxide. That means we are going to obtain an anti-Markovnikov product. So usually the Br minus, the negative part of the addendum, should go attached to the most substituted carbon, that is this carbon. But since the reaction is going to be anti-Markovnikov, the Br minus is going to attach in this carbon and hydrogen would come here. Okay. And the product that we then obtain will be CH3, CH2, CH2, Br. So that will be our product B, which is an anti-Markovnikov product. And the next reaction is with sodium iodide in dry ether. So that is going to be a substitution reaction. That means the bromine that is present here is going to get substituted with the iodine. So that is a way to prepare alkyl iodides. So in that case, we will be getting the product where the bromine gets substituted by iodine. So our product will be CH3, CH2, CH2I. So propyl iodide will be the product that is obtained. And then the final step is the reaction of this alkyl iodide with magnesium in dry ether. So that is the method of preparation for Grignard reagent, which is of the general formula RMgX. That means the magnesium here is going to get attached between the alkyl group and the halogen that is taken here. And the corresponding Grignard reagent will be obtained. That means we will be getting CH3, CH2, CH2, Mg, I. So this is the sequence of reaction that is happening here. We have been asked to write the structural formulas of the compounds A, B, C and D. So this alkene, that is our first product A, and this bromide is our second product B. The iodide replaced one, that is C, and the Grignard reagent that is obtained in the final step, that is our product B. So this is a sequence of reaction that is happening here. Our end product is a Grignard reagent, which is of the general formula RMgX. And we have an option for this question. So you can either answer those first set of questions or you can go with these questions. So in this question, we have to explain three statements. The first statement, the dipole moment of chlorobenzene is lower than that of cyclohexyl chloride. So if you take chlorobenzene, in the structure of chlorobenzene, you can see that the carbon halogen bond here, the carbon halogen bond here will have a partial double bond character due to the resonance that is happening. Means the electrons that is present in chlorine will be donated towards the ring, and due to a series of resonance structures that is formed, the carbon halogen bond will have a partial double bond character, which means the polarity of bond is comparatively lesser compared to that of cyclohexyl chloride, in which we only have a cyclohexane ring. That means the carbon halogen bond here is going to be more polar than the bond that is present in the case of chlorobenzene. So the dipole moment of chlorobenzene is going to be lower than that of cyclohexyl chloride. The next statement, alkyl halides, though polar, are immiscible with water. So we know that water is a polar molecule. Alkyl halides are also polar in nature, but they are not miscible with each other. As you know, there is a strong possibility for hydrogen bonding in the case of water. So water molecules are bound together through hydrogen bond. But in the case of alkyl halide, the molecule is going to exist as a dipole. So the type of interaction that is happening in the case of alkyl halides will be dipole-dipole interactions. But in the case of water, the intermolecular attraction happening is hydrogen bonding. So we know that hydrogen bonding is a stronger force of attraction than dipole-dipole interactions. So even though there are interactions between the molecules and both the molecules are polar, the magnitude of interactions are different in the case of alkyl halides and water. That is more in the case of water and comparatively lesser in the case of alkyl halides. So there is no way that there is going to be new interaction between one alkyl halide molecule and one water molecule. So that is why even though both of them are polar, there is no miscibility between water and alkyl halides. The third statement, Grignard reagent should be prepared under anhydrous conditions. So there should not be any presence of water or moisture during the preparation of Grignard reagent. If yes, the Grignard reagent which is written in the general formula RMgX, that is going to react with water, or even if a tiny amount of moisture is present, that is going to have a reaction. So the Grignard reagent that we take will be converted into the corresponding hydrocarbon. That means we will be getting the product RH and the byproduct MgOHX. So there should not be presence of water or moisture during the preparation of Grignard reagent. If yes, any amount of water or moisture is present, then this reaction will happen and we will be losing the Grignard reagent that we prepared. So that is why all the reactions and preparation of Grignard reagent is carried out in dry ether medium where there is no presence of water or moisture in any ways. So we have given the explanations for all the three statements. So we can move on to the next question. 28th question. It is a question from electrochemistry. What is limiting molar conductivity? Why is there a steep rise in molar conductivity of weak electrolytes on dilution? Let us take a look at the first part of the question. What is limiting molar conductivity? We know that limiting molar conductivity of an electrolytic solution is the conductivity of that electrolytic solution at an infinite dilution or when the concentration of the solution approaches zero. So that is called as the limiting molar conductivity. And we know that there are two kinds of electrolytes. We have strong electrolytes and weak electrolytes. So if you take the case of a strong electrolyte, we can see that the molecule will be completely ionized. That means the molecule will be existing as ions. Whereas in the case of weak electrolyte, the dissociation, the extent of dissociation is comparatively lesser. So if you are diluting a solution of strong electrolyte, the increase in conductivity will be only due to the reason of that dilution. That means the rate of increase of conductivity will be comparatively lesser, or it will be following an almost linear path, which is proportional to the root of concentration of the solution that is taken. Whereas in the case of weak electrolyte, as we dilute the solution, the increase in conductance or conductivity, that is due to the increase in ionization of the electrolyte that is taken. So that increase is going to be a more significant increase than in the case of a strong electrolyte, which happens only due to the dilution. So that is why there is a steep rise in molar conductivity in the case of weak electrolyte, in the case of dilution, and the value of limiting molar conductivity cannot be determined through a graphical method. That's why we are going to take the help of Kohlrausch's law to find the limiting molar conductivity in the case of weak electrolytes. So that's our explanation. And the B part of the question, calculate the EMF of the following cell at 298 Kelvin. So here we have magnesium taken as the anode and we have copper that is taken as the cathode. So you have to find the EMF of this cell, and we are given the reduction potential of copper and magnesium. The reduction potential of copper is plus 34 volt. Copper is actually the only metal which has a positive reduction potential. And in the case of magnesium, the standard reduction potential is minus 2.37 volt. So magnesium, that is going to act as the anode, and copper, which has a higher reduction potential, that is going to act as the cathode. So we have to find the EMF of the cell. We know the equation to find the EMF of a cell, that is given as E cell, that is the EMF of the cell under non-standard conditions. You can see that the cell that is given here is under non-standard condition because the concentration of the electrolytes is not 1 molar, it is 0.1 molar and 10 raised to minus 3 molar in anode and cathode respectively. So that is under a non-standard condition. So we'll have to use the equation E cell is equal to E0 cell minus 0.0591. That is the value of RT divided by F divided by N. N is the number of electrons that is involved in the reaction multiplied by the log concentration of anodic species by cathodic species raised to their corresponding stoichiometric coefficients. So the anodic species here is magnesium 2 plus, and the cathodic species is copper 2 plus, copper ion. So the corresponding concentration will be 0.1 molar and 10 raised to minus 3 molar. And the number of electrons involved here is obviously 2, because magnesium is getting converted into magnesium 2 plus and copper 2 plus is getting reduced into copper. So the value of N is 2. So to find E0 cell, we have to do the potential of cathode minus anode. So that will be cathode minus anode value will be 0.34 minus of minus 2.37. So this value will be E0 cell will be 0.34, that is the cathode potential, minus of minus 2.37. And that minus 0.0591 divided by number of electrons involved is 2 multiplied by log concentration of anodic species, that is concentration of magnesium, that is 0.1 molar, and in the case of cathode that is 10 raised to minus 3 molar. So that is going to be log 0.1 is 10 raised to minus 1 divided by 10 raised to minus 3. Right. So this will be log of 10 raised to 2, that will be 2. Right. So this 2 and this 2 is going to get cancelled. So this will be 2.37 plus 0.34, which will be 2.71. So E0 cell here in the case is 2.71 minus 0.0591. So we just have to find out the difference between these two values, that is 2.71 minus 0.0591, and that will be our answer. Right. So that is going to be 9, 0, 5 and 6. That is 2.6509 volt will be our answer, but we need to write the answer in only 2 decimal values, so we can round off this value to 2.65 volt. So that will be the potential of the electrochemical cell that is formed here. The answer will be 2.65 volt. So that is our answer. And we can move on to the next question now, the 29th question. A question from coordination compounds. Give the formula of each of the following coordination entities. Not only we have to write the formula, we'll have to write the name, the magnetic behavior of these coordination entities. Right, the first compound, cobalt 3 plus ion is bound to 1 chlorine, 1 ammonia molecule and 2 bidentate ethylene diamine molecule. So our central metal atom is cobalt 3 plus. Right. So we are looking for the first compound. So our central metal atom is cobalt 3 plus. And which are the ligands that we have? We have 1 chlorine, 1 ammonia and 2 ethylene diamine ligands. Okay. So we have 1 ammonia, 1 chlorine and 2 ethylene diamine as ligands. So that will be all about our coordination sphere. And ethylene diamine and ammonia are neutral ligands. They do not have a charge. And chlorine has 1 negative charge. And cobalt is in the +3 oxidation state. That means our total coordination sphere is going to have a charge of +2. All right. And we also have to write the name and magnetic behavior of this coordination compound. So in the case of cobalt 3 plus and ammonia is coming as a ligand, So in this case, ammonia is going to act as a strong ligand. That means the pairing of electron is going to take place. So we have to know the electronic configuration of cobalt 3 plus. Cobalt, as you know, it is D7 configuration. So if you take cobalt 3 plus, the configuration will be 4s0 and 3d6. So cobalt 3 plus will be having a 3d6 configuration. As the ligand here is going to act as strong ligands, the electrons will be paired. So there will be no unpaired electrons. So since there is no unpaired electron, the compound is going to be diamagnetic in nature. Since there are no unpaired electrons, the compound is going to be diamagnetic in nature. And we have to write the name of this compound. So how do you write the name of this compound? Now the coordination sphere is positively charged. So we can start with the writing the names of ligands in alphabetical order, and then the name of the central metal ion and its oxidation state in square brackets. So we have amine, chlorido and ethylene diamine. We have amine, chlorido and ethylene diamine. So we can follow this alphabetical order. So we start with the ligands. So that will be amine, and then C, chlorine, chlorido. We have two ethylene diamines. So that will be bis-ethylene diamine. Bis-ethylene diamine. So that is all about the ligands, and then the central metal atom, that is cobalt. Cobalt and oxidation state in brackets in Roman letter, cobalt 3. So that is the name of our compound. You can mention it is an ion also. So that is the name of the first coordination species that is written, right? So similarly, we have to follow the same steps for the second compounds also. In the second case, that is a nickel 2 plus ion that is bound to two water molecules and two oxalate ions. So nickel is our central metal atom, and we have water and oxalate that is coming as the ligand. So both of them are weak ligands. Both water and oxalate is going to act as weak ligands. So let us see how we can write the name and we can define the magnetic property of the second compound. Now nickel has a D8 configuration, so nickel 2 plus will also have a 3D8 configuration. And since both the ligands are weak ligands, there is no pairing of electrons happening. So first we can write the formula and then the name and magnetic behavior. So magnetic behavior, obviously it is going to be paramagnetic in nature because there will be presence of unpaired electrons. Right. So we have to write the formula of the compound then. Nickel is our central metal atom, and then we have water and oxalate as the ligands. So we have two water molecules, that is H2O twice, and two oxalate ions, that is C2O4 the twice. So that will be our coordination sphere. Water, here is a neutral ligand that has no charge. C2O4 has a charge of 2 minus, so the total charge is -4. Nickel is in the +2 oxidation state. That means the total charge of the coordination sphere will be negative. The coordination sphere has a -2 charge. You should not forget to write the charge of the coordination sphere along with the molecular formula. So this is an anionic complex, so its name is going to end in AT. Right. So we can now give the name to this compound. So this is aqua starting with A, and this is oxalato starting with O. Right. So two water and two oxalate. So it will be diaqua, dioxalato. So the ligands are done, and nickel 2 plus. Since the complex is negatively charged, the name should end as nickelate, and the oxidation state of nickel, that is 2. That is the name. And since there will be unpaired electrons present, the magnetic nature, that will be paramagnetic in nature. So we answered all the questions. Now the next question, 30th question. What is crystal field splitting energy? How does the magnitude of octahedral splitting energy, that is delta octahedral, decide the actual configuration of d orbitals in a coordination entity? So what is crystal field splitting energy? We know that in the absence of ligands, all the 5 d orbitals are degenerate, whereas in the presence of ligands, the degeneracy of this d orbitals is lifted and they are going to get split into 2 set of orbitals as T2 and E set of orbitals. So the difference in energy between these 2 sets of orbitals is called as the crystal field splitting energy, or CFSE. So the magnitude of that splitting depends upon the strength of the ligand that is coming, and the type of splitting depends upon the type of compound that is formed, whether the compound is going to be square planar, octahedral or tetrahedral. Right? And how does the magnitude of delta octahedral decide the actual configuration of d orbitals in a coordination entity or coordination species? So there will be a comparison between the splitting energy and the pairing energy that is happening here. So here we are specifically asked about the octahedral splitting. So let us write this with the help of an example. Suppose that we have a coordination species which is going to have a D4 configuration. So the splitting will be like T2G set and EG set. So the T2G set will have a lower energy and EG set will have a higher energy. So the first 3 electrons are going to go in the T2G set, and the 4th electron do have a choice. It can either pair here or it can come to the EG set of orbitals. So that happens after a comparison between the 2 values, the crystal field splitting energy and pairing energy. That means there is an amount of energy that is required to pair the electron in the T2G set of orbital. So whichever value is lower, that process will be naturally preferred. Right? Suppose that pairing energy is lower, then pairing of electrons is going to happen and the configuration will be a low spin configuration. Suppose that the splitting is lower, the octahedral splitting energy is lower, then the pairing will not be preferred and we will be obtaining a high spin complex with this D4 configuration. Right? So the actual configuration of orbitals, that is actually explained by the comparison of these 2 energies, the crystal field splitting energy and pairing energy. Right? If the pairing energy is greater, then we will be obtaining a high spin complex or a high spin configuration where the electron will be placed in the higher energy orbital. Or in the second case, suppose that the splitting energy is higher and the pairing energy is lower, and then obviously pairing will be preferred and we will be obtaining a low spin configuration. So that is how the placement of electrons in the orbitals is explained by the comparison between the crystal field splitting energy and the pairing energy. So that is one set of questions, and we have a choice. We can either answer the first 2 questions or you can answer this set of questions. So here we have to describe the shape, hybridization and magnetic behavior of the following complexes. So both the questions are from coordination chemistry. So we have 3 complexes here. We have to write the shape, hybridization and magnetic behavior. So let us write the names of 3 compounds. The first compound we have CONH3 6 times 3 plus. The second compound is NiCN4 2 minus, NiCN4 2 minus, and the third compound is COF6 3 minus. So in this case, cobalt is the central metal atom which is in the 3 plus oxidation state. So the configuration is going to be 3d6. In the second compound, nickel is in the plus 2 oxidation state and the configuration is going to be 3d8. And here also cobalt is in the plus 3 oxidation state. So the configuration is going to be 3d6. So when cobalt is in the plus 3 oxidation state and when ammonia is coming as a ligand, ammonia will be acting as a strong ligand. So the ligand here, it is strong. Here also cyanide is a strong ligand. And in the third case, it is fluorine which is coming as the ligand, which is a weak ligand. Right. So now we have to find out the shape, hybridization and magnetic behavior. So since we have a D6 configuration in the first compound and the ligand is strong, the D6 configuration can be written as 1, 2, 3, 5, 6. Right. And now we require 6 empty orbitals. So that will be the 2 3d orbitals and then 4s and 3 4p orbitals. That means the hybridization is going to be D2sp3 hybridization, and the shape of the geometry of the compound or the complex will be octahedral geometry. Right. Now in the second compound, nickel is in the +2 oxidation state and configuration is electronic configuration is 3d8. Now since cyanide is a strong ligand, there also the pairing of electron is going to take place. So the 3d8 configuration will be written like this. And we only have 4 ligands, so we need 4 empty orbitals. So that is going to be 1 3d orbital, 1 4s orbital and 2 4p orbital. So the hybridization is going to be dsp2 hybridization. Since the hybridization is dsp2, the geometry of the compound will be square planar. It will be of square planar geometry. And the last compound, in that case the ligand is a weak ligand and the cobalt is in the +3 oxidation state, and so the configuration is going to be 3d6. But in this case, since the ligand is weak, the pairing of electrons is not going to take place. That means the d6 configuration can be written like this. So we have 4 unpaired electrons that is present, and the hybridization cannot use these d orbitals. So the next vacant orbitals will be used. That means the 4s, 4p and 4d orbitals will be used. So 1s, 3p's and 2d's will be used. That means hybridization will be sp3d2. In that case also the geometry of the molecule is going to be octahedral. Right. So we have compared all the 3 compounds and we have written the shape, hybridization, and we also have to explain the magnetic behavior. So in the first compound there is no unpaired electrons. That means the compound is going to be diamagnetic in nature. In the second compound also we have no unpaired electrons, so that is also a diamagnetic complex. Only in the third compound there is a presence of unpaired electrons, so that is going to be paramagnetic in nature. And since we have 4 unpaired electrons, we can also find the value of spin magnetic moment. That will be root of 4 into 4 plus 2. That means root of 24. Bohr magneton. That will be the value of spin only magnetic moment. So we have compared the shape, hybridization and magnetic properties of all the 3 compounds that has been asked in the question. So that winds up our third section, section C. We can move on to the next section, section D. In this section, we have to read the passage and we will have to answer the questions that follows. Now, there may not be necessarily a direct relation between the information that is given in the passage and the questions that has been asked. Right? So, the first passage that is about the evidence for the fibrous nature of DNA, that says a lot about DNA. The types of bases that is present. We have both purine and pyrimidine bases, the types of bases that is present in DNA. And it also says about a 5th base, that is 5-methyl cytosine, that occurs in certain organisms. And DNA has some features which are regular and some features are irregular. And the whole passage is about the DNA. So let us take a look at the questions that has been asked. The first question, we have 3 questions here. The first question, the 2 strands of DNA are complementary to each other, give reason. The second question, the difference between a nucleoside and a nucleotide, which is not mentioned in the passage, and give the structural differences between RNA and DNA. So you can see that the questions that is asked after the passage may not necessarily be directly from the passage. So we can start answering the questions directly if we know the answers for them. The first question, the 2 strands in DNA are complementary to each other. Right? So we know that the structure of DNA is a double helical structure and they are held together by hydrogen bonds. The 2 strands are held together by hydrogen bonds through AT and GC pairs. So adenine bonds with thymine and guanine bonds with cytosine, they are linked together through hydrogen bonds. So that is why the two strands are called complementary to each other. Second question, what is the difference between a nucleoside and a nucleotide? So that is a question that is directly from the textbook. We can differentiate between a nucleoside and a nucleotide. So nucleoside is a more simpler structure that is found by the attachment of a base on the 1' position of a sugar. So nucleoside consists only of a base and a sugar. And if it has to get converted into a nucleotide, then a phosphate group will also have to attach. That means a phosphoric acid is going to come extra and going to get attached in the 5' position. And then the nucleoside will be converted into a nucleotide. Means a nucleoside consists only of a base and the sugar molecule. And the nucleotide will be consisting of a base, the sugar molecule, and there is also a phosphate linkage. There is also a phosphate linkage that is extra present in the nucleotide. Right. So you can see the carbons in the sugar that is numbered as 1', 2' because there are also carbons present in the base which has to be numbered. So in order to differentiate between the carbons in the base and in the sugar, the carbons in the sugar are numbered with a dash on top. And these nucleotides are joined together by phosphodiester linkage that is happening between the 5th and 3rd carbon atoms of the pentose sugar that is present. So that is the difference between a nucleoside and a nucleotide. So that answers our second question, the difference between a nucleoside and a nucleotide. We have one more question remaining, that is to give the structural differences between RNA and DNA. So we know RNA is ribonucleic acid and DNA is deoxyribonucleic acid. The main difference, structural difference between RNA and DNA is that RNA is a single-stranded structure but DNA has a double helical structure and which is held together by hydrogen bond. So the bonding pairs that is present in DNA is AT and GC. So adenine and thymine and guanine and cytosine are the complementary pairs that is present in the case of DNA. Whereas in the case of RNA, thymine has been replaced by uracil. That means the complementary pairs are adenine, uracil and guanine cytosine pairs which is present in RNA. And also there is a difference in the sugar that is present which is evident from the name. The sugar that is present in RNA is ribose, which is called ribonucleic acid, and the sugar that is present in DNA, it is called deoxyribose and hence the name deoxyribonucleic acid. Okay. So that is the structural differences between DNA and RNA. So we have answered all the questions that follows one passage and there is another question, another passage and another set of questions which we will have to answer. So this one is from kinetics which says about the Arrhenius equation. So it says that Arrhenius studies the effect of temperature on a rate of reaction and postulated a rate constant which varies with temperature. So he said that the rate of the reaction varies with temperature and the famous Arrhenius equation is given. And for most of the reaction, it was found that the temperature coefficient lies between 2 and 3, alright. Keeping the temperature constant, the effect of catalyst on the activation energy has also been studied. By how much the rate of reaction changes in activation barrier and increases the rate of the reaction. So it says that the catalyst increases the rate of the reaction by decreasing the activation energy of the reaction. So let us see if the questions can be answered directly from the passage or not. The first question is to define the activation energy of the reaction. So the activation energy of the reaction, and the second question, what does the factor e raised to minus Ea by RT in the Arrhenius equation? We have the Arrhenius equation which is K is equal to the rate of the reaction, K is equal to A into minus Ea by RT, A is the Arrhenius factor. And what does this fraction e raised to minus Ea by RT indicates is the second question. And thirdly, we have to draw a plot for log K and 1 by T in the case of a chemical reaction, and also what is the relation between slope and the activation energy obtained in that graph. So the first question, define the activation energy of a reaction. So that activation energy is the minimum energy that the reactant should possess so that it could get converted into products, or that is the amount of energy that is required for the formation of the activated complex or the transition state in a reaction. Right? So only those molecules having activation energy or a greater amount of energy will be getting converted into products. And what is the factor e raised to minus EA by RT indicates? In the Arrhenius equation, this factor indicates the fraction of molecules or the amount of molecules having an energy which is equal to or greater than the activation energy. So those fraction of molecules are going to get converted into products. Right. And now about the graph, we have to draw a plot between the log of rate constant K versus 1 by T for a chemical reaction. Right. And also what is the relation between the slope of the graph and activation energy of the reaction. Right. So we can plot the graph. So we can start from the Arrhenius equation which goes like K is equal to A into e raised to minus EA by RT. So take log on both sides. So we will be getting ln K is equal to ln A plus ln and E gets cancelled minus EA divided by RT, which can be rearranged as ln K is equal to minus EA divided by RT plus ln A. So which is in line with the equation of the straight line y is equal to m into x plus c. So our y-intercept c is going to be ln A. So this is our intercept, this value it is going to be ln A. So our plot is between the logarithmic value of the rate constant and the inverse of temperature 1 by T. Right. So this is 1 by T. 1 by T is our x factor here. So the remaining value minus EA divided by R. Minus EA divided by R is going to be the slope which is m. So the slope of the graph that we obtain is minus EA divided by R. So you have been asked what is the relationship between the slope and activation energy. So the relation between these two values is given as the slope of the graph that we obtain, that is given as minus EA divided by R. So slope is equal to minus EA divided by R. So that is the relation between the two quantities that has been asked. Okay. And we have a choice for that question in the C part. This is a numerical question. The question goes like, in general, it is observed that rate of a chemical reaction doubles with every 10-degree rise in temperature. That is a known fact. And if this generalization holds true or good for the reaction temperature which ranges from 295 Kelvin to 305 Kelvin, what would be the value of activation energy for this reaction? Right. So we have to compare the rate constants at two different temperatures and find the value of activation energy. The known constants are given. The value of R is 8.314 and log 2, value of log 2 is 0.3010. So we'll have to find the activation energy by comparing the rate constant at two different temperatures. For that we can use the equation which goes like log K2 by K1 is equal to EA by 2.303 R into 1 by T1 minus 1 by T2. So we can substitute the values here. It is given that for a 10-degree rise in temperature, the rate constant is going to get doubled. That means K2 will be 2 times that of K1. So LHS of our equation will be ln 2 divided by 1, which is log 2. So we have to find the value of EA divided by 2.303. The value of R is 8.314 into the first temperature is 295 Kelvin and the second temperature is 305 Kelvin. Right. So this can be simplified as 305 minus 295. So that will be 10 divided by 295 into 305. So from this we can find the value of activation energy. The value of log 2 is given. It is given as 0.3010 into 2.303 into 8.314 multiplied by 295 and 305 will come up in the top and divided by 10. So that will give you the value of activation energy here. So this is the value of activation energy. And to the simplification, we will be getting the answer as 51.85 kilojoule per mole. So that will be our final answer for the value of activation energy. So activation energy of the reaction is 51.85 kilojoule per mole. Right. So it's a simple equation, it's a very basic equation. The substitutions are also easy. Right. So do the simplifications correctly and you will be getting the correct answer for activation energy. Right. So our fourth section, the section D is also over. We are moving on to the final section of the question paper, that is section E. So all the questions here are 5-mark questions and there will be a lot of sub-questions. Right. So our 33rd question and the A part in that question, that again has subsections. The first question, give the IUPAC name of the compound that is given here. Right. So this is cyclohexane ring, that is our base here. And we have two substituents here. We have a ethoxy group. So this one is our ethoxy group and we have a nitro group that is present as the substituent. Right. So if we look at the priority for the substituent groups, we can see that the methoxy groups are always coming as prefix substituents. Right. And the second substituent is a nitro group. Right. So we'll have to start the numbering of carbon atoms from here, which is going to come as a prefix. So this will be the second carbon, 3, 4, 5 and 6. Right. So our substitutions are ethoxy group in the first carbon and nitro group in the second carbon. The naming is not reverse. You should not name the compound as 1 nitro and 2 ethoxy. This is wrong because the alkoxy group is always going to come as a prefix. Right. So the first compound, that is ethoxy and nitro. And when we have two substituents, we will have to follow the alphabetical order. In that case, this starts with E and this starts with N. So ethoxy comes first. So the name of the compound will be 1 ethoxy, 2 nitro. What is our base compound? That is cyclohexane. Cyclohexane, that is the IUPAC name of the compound, and it is not 1 nitro 2 ethoxy cyclohexane. That is a common mistake that has been made. So that is the IUPAC name of the compound that is given here. The second question, how can acetone be converted into propane? How can acetone be converted into propane? Give the name of the reaction and illustrate the necessary steps. Right. So we have to convert acetone, which is CH3, CO, CH3 into propane. That means CH3, CH2, CH3. That means the carbonyl group that is present will have to be converted into a CH2 group. So what is that reaction called? That is the Wolff-Kishner reduction, which converts the carbonyl group into a CH2 group. Right. So this is the reaction. The name of the reaction is Wolff-Kishner reduction. Okay. So we start with the acetone. We have a carbonyl group that is present. The first step is to react the carbonyl compound that we have taken with a hydrazine. This is hydrazine, NH2, NH2. Right. And then the second step is the reaction with the potassium hydroxide in ethylene glycol. The boiling point of the solvent is very high and then we have to heat it. And then we will be obtaining the required compound propane. We can see that the carbonyl group that is present here, that is getting converted into a CH2 group and nitrogen gas will be eliminated. So name of the reaction is Wolff-Kishner reduction. This is the steps that we have to follow. This is a two-step reaction. First is the reaction with the hydrazine and the second step is the reaction with the KOH in a high boiling solvent like ethylene glycol. Okay. And the B part of the same question, right. Here we have to give reasons for the two statements that is given here. We have an internal choice in this question. So we can either answer these two set of questions or the next set of questions. Right. So the first question, aldehydes are more reactive than ketone towards nucleophilic addition reaction. Aldehydes are more reactive than ketones. Right. So if we take the case of aldehydes, the general formula is RCHO. And in the case of ketones, we have two alkyl groups. We have R, C double bond O and R dash. Right. So when a nucleophile comes, that is Nu minus comes, that is going to come and attack the carbonyl carbon which has a partial positive charge. So the chances for the nucleophile to come and attack the carbonyl carbon in the aldehyde is much greater than in the case of ketones, because in the case of ketones there are two alkyl groups which are going to pose a steric hindrance. So for that reason aldehydes will be more reactive than ketones towards nucleophilic addition reaction. The second question, the pKa of 4-nitrobenzoic acid is less than that of 4-methoxybenzoic acid. So if we are taking benzoic acid, the first substituent, in the case of first compound, the substituent is a nitro group which is an electron withdrawing group. And the case of the second compound for methoxybenzoic acid, we have methoxy group which is an electron donating group. Statement says that the pKa of 4-nitrobenzoic acid is lesser, which means 4-nitrobenzoic acid is a stronger acid or which is more acidic than 4-methoxybenzoic acid. So what would be the reason? In the first compound we have an electron withdrawing group that is present. So the presence of an electron withdrawing group in an aromatic acid, that will stabilize the carboxylate anion that is found by taking away the electron density from the benzene ring. So that is why 4-nitrobenzoic acid will be more acidic than the second compound which has an electron donating group. So in this case, the carboxylate anion that is formed here, that will be made less stable by the presence of the methoxy group that is present, because methoxy group is an electron donating group, and hence the acidity of that compound will be lesser than the first compound, which means it will be having a higher pKa value. The second compound will be having a higher pKa value, which means it is less acidic. So that is one set of questions. So we can either that two questions or this is a choice, and that has three sub questions. A compound X which has a molecular formula C2H4O2 that undergoes haloform reaction, and on treatment with hydrogen cyanide, the first compound X forms a product Y that on hydrolysis gives 2-hydroxypropanoic acid. So this is a series of reaction that is happening. We have a compound with a particular molecular formula. The first reaction is with a hydrogen cyanide which gives a product Y, and that on hydrolysis gives you a carboxylic acid. So we have been asked to write the structure of X and Y. Will X undergo an aldol reaction, and if yes, why? The third question, write down the equations for the corresponding reactions that is involved. So if we take a look at the molecular formula, this is C2H4O2. So the molecular formula C2H4O2 means that it can either be an aldehyde or it can be a carboxylic acid. So this molecular formula can either be CH3CHO, ethanaldehyde, or it can be a carboxylic acid which is CH3COOH. So we have to determine whether the compound is going to be an aldehyde or a carboxylic acid. So if it undergoes haloform reaction, then obviously the starting material would not be a carboxylic acid, it will be an aldehyde. So starting material is ethanaldehyde. So first we will have to write the reaction of ethanaldehyde with hydrogen cyanide, and then its hydrolysis will give you 2-hydroxypropanoic acid. So let us see. So C2H4, it can either be an acid or an aldehyde. So we have confirmed that that is an aldehyde. So we'll be taking the aldehyde which is CH3CHO. The first reaction is its reaction with the hydrogen cyanide, HCl. So in that case, on reaction with hydrogen cyanide, cyanohydrin will be formed, which is a very important intermediate which is highly useful in the case of synthesis of other compounds. Right? So this HCN is going to get added on either sides of the carbonyl bond. So that means CH3 C double bond OH is going to get converted. So the H plus is going to get attached here. So this will become OH, and the Cn minus will be attached to the carbonyl carbon which is positively charged, and the double bond here will be lost. So that is the corresponding cyanohydrin that will be formed. And on the next step, the hydrolysis, in the hydrolysis of that step, we will be obtaining 2-hydroxypropanoic acid. 2-hydroxypropanoic acid. That means the CN group that is present here, that is going to get converted into a carboxylic acid group, and the product that we obtain will be CH3 CH OH CO OH. So the product will be 2-hydroxy. 1, 2 and 3. We have 2-hydroxypropanoic acid which is obtained as the final product. So this is the reaction that is going on here. We have to write one more reaction. It is also mentioned in the question that our given compound undergoes haloform reaction. So we also have to write the haloform reaction that is happening. Right. So haloform reaction of the aldehyde, that is ethanaldehyde with the sodium hypohalide. So that is the reaction that we want. CH3 CHO. That is going to react with the sodium hypohalide. Right. NaOX. That is sodium hypohalide. And we will be obtaining haloform. So in this case, CH3X will be formed as the product. That is CH3X, which is our required haloform, and the corresponding carboxylic acid from the remaining part, that will be formic acid or HCOH. So this is the haloform reaction that is happening, and this is the haloform that we have obtained as a end product. So this is a series of reactions that is happening. So we have drawn the structures of X and Y. So we now know that X is ethanaldehyde, and we also got the structure of the cyanohydrin, that is Y. And then we wrote the corresponding equations where the reactions are involved. And will X undergo aldol reaction? Yes, this is an aldehyde which is having alpha hydrogens. Right? So if alpha hydrogens are present, aldehydes and ketones which has alpha hydrogen presence, they will be undergoing aldol reaction and will be getting the corresponding aldol products and aldol condensation products. So due to the presence of alpha hydrogens, the compound X that we have taken, that will be undergoing aldol reaction and will be getting the corresponding condensation products. So that answers all the questions that have been asked here. So this is a choice question. So we can either answer the first two questions or we can answer these three questions. The B part of the question, give the chemical test to distinguish between the following pairs of compounds. The first set of compounds is propanol and propanone, and the second set of compounds is acetophenone and benzophenone. So first, what is the test to distinguish between an aldehyde and a ketone? And the second question, in that case, both of them are ketone. First one contains an alkyl group, whereas the second compound contains two benzyl groups. So how would we distinguish between the compounds? So to distinguish between propanol and propanone, that means an aldehyde and a ketone. If you take the case of aldehyde, the propanol, that will give a silver mirror test. That is, it will give a positive test with a tolerance reagent, that is ammoniacal silver nitrate. Whereas propanone will give you the iodoform test. Propanone will give you the iodoform test, whereas propanol will not give the iodoform test. So that is how we could differentiate between an aliphatic aldehyde and an aliphatic ketone. That means the tolerance reagent test, that is a silver mirror test, is given only by an aldehyde and not by ketone, whereas the second test, the iodoform test, is given by the ketone but not by the aldehyde. And similarly, we can differentiate between acetophenone and benzophenone by the same second test, that is by the iodoform test or the haloform test, which is the reaction between a sodium hypohalide. In that case, only those compounds which contain a CH3CO group will give you a positive iodoform test or a haloform test. So that is why you can see that only benzophenone will not give you the iodoform test. That is acetophenone, which contains the CH3CO group, that will give you a positive iodoform test, whereas you can see that benzophenone will not give you that test. So this is how we can differentiate between the given two sets of compounds. The next question, 34th question, that is a question from electrochemistry. Express a relationship among cell constant, resistance of the solution in the cell, and conductivity of the solution. So we have to find a relationship between cell constant, resistance, and the conductivity of the solution. And how is molar conductivity of a solution related to the conductivity? How is molar conductivity and conductivity of a solution related? So let us see how we can answer this question. So we have to start with the relationship between conductance and resistance. We know that conductance and resistance are inverses or reciprocals of each other. So we can write that conductance G is equal to 1 by R, or we can write R is equal to 1 by G. Let's write that resistance R is equal to 1 by G. Now we know the equation of resistance. R is given as R is equal to rho L by A, where rho is the resistivity of the material and L by A is called as the cell constant. So we can write this as rho into L by A, which is the cell constant. Rho is the resistivity and L by A is the cell constant, which is represented as G star. So we can write this as rho into G star, right? So the equation now changes to, instead of R, we can write rho into G star. Rho into G star is equal to 1 by G, or we can take this G up to the other side, that is conductance into cell constant, that is equal to 1 by rho, and this 1 by rho is nothing but the conductivity of the solution, which is represented as kappa. So the required relation is that conductance into cell constant, that will give you the conductivity of the solution. So that is the first part, and the second part, it is asked that how is molar conductivity and conductivity of a solution related. So we know that the molar conductivity of a solution is the conductivity of a solution having a unit concentration. So if you want to find out molar conductivity, we just have to divide the conductivity by the concentration of the solution. So we can write that the molar conductivity lambda m, it can be represented as conductivity kappa divided by the concentration of the solution. So when expressed in the terms of molarity, we can write it as kappa divided by molarity of the solution and multiplied by a factor of 1000, because there is a conversion factor into liters. And what is the unit? The unit is Siemens centimeter square mole inverse. So this is the required relationship between the given quantities and the relationship between the conductivity and molar conductivity of a solution. Now the B part of the same question. The cell in which the following reaction occurs, you can see that Fe3 plus is being converted into Fe2 plus and I minus is being converted into iodine. Now the cell potential of this cell is given as 0.236 volt, 298 Kelvin. We have to calculate the standard Gibbs energy change and the equilibrium constant for the given cell reaction. So we have to find Gibbs energy and the equilibrium constant Kc. Right, so we know the equation of Gibbs free energy, that is given as delta G is equal to minus NF E cell. So if it is under standard condition, we can write it as G0 and E0. Now we have to find the equilibrium constant Kc. So for that we have the equation E0 cell is equal to RT by NF into ln K. ln K or ln Kc, which is the equilibrium constant. So first we can find the Gibbs free energy and then we can find the value for equilibrium constant. Now we know that the cell potential, this is cell potential 0.36 volt, that is given. So how can we find the value of Gibbs free energy? It can be given as minus NFE0 cell. So we know the value of F, that is 96,500 coulombs, and N is the number of electrons that is involved in the reaction. We can easily say that the number of electrons involved here is 2 electrons, because we have 2 I minus that is being converted into iodine. So there is 2 electrons involved here, and similarly 2 Fe3 plus is being converted into 2 Fe2 plus. So the total number of electrons involved in the balanced chemical reaction is 2 electrons, because 3 plus is being converted into 2 plus, but we have 2 molecules. So the total number of electrons involved is 2. Alright. So what will be the value of delta G? The value of delta G will be minus 2 into 96,500 into what is a given E cell, that is 0.236. So that will give you the value of Gibbs free energy, that is delta G. So from this equation we can calculate the value of delta G. We will obtain the value of delta G as minus 45.548 kilojoules. So that will be the value of delta G that we obtain. And secondly, we have been asked to find out the value for equilibrium constant Kc. For that we can use the second equation. So we already know the value of E0 cell, that is given as 0.236, and the value of RT divided by F, that can be written as 0.059, that is the simplified value of RT divided by F. So we can write instead of RT divided by F, we can write it as 0.0591 divided by the value of N is 2 and multiplied by, if you want to convert it into base 10 logarithm, we can multiply it with a 2.303. And how can we find the value of Kc? That is the value we have to find out, right? So the value of log Kc will be 0.236 into 2 divided by 2.303 into 0.0591, and that will be the value of log Kc. That will be the value of log Kc, and log Kc will be obtained as, after simplification, we will get the value as 7.986, but we have to find the value of Kc, right? Since we have the value of log K, we can write the value of Kc or K as 10 raised to 7.986. Since we cannot find the anti-log value directly without the help of logarithm table, it is enough that we write the value of Kc as 10 raised to the value of log value that we have obtained, right? So we have found out the value of Gibbs free energy and the value of equilibrium constant, which has been asked in the question. Right. So you can either answer that part of the question, or we have a choice, another set of questions that we can answer here. And that has 4 sub-questions. The first question is to state the Faraday's first law of electrolysis. And the second question, predict the products of electrolysis of an aqueous solution of sulfuric acid using platinum electrode. What will be the products that will be obtained in the anode and cathode as a result of oxidation and reduction reactions? And the third question, we consider the given reaction. So we have dichromate ion that is being converted into Cr3+. What is the quantity of electricity in coulombs needed to reduce 1 mole of this dichromate ion? So let us see, we can answer these questions one by one. The first question says the Faraday's first law of electrolysis. So when we write the statement for this law, the statement should be accurate. So what does it say? Faraday's first law of electrolysis says that the amount of chemical reaction which occurs at any electrode during electrolysis by a particular value of current, that will be proportional to the quantity of electricity passed through the electrolyte. So mathematically we can write that the weight of the product that is obtained at a particular electrode, that will be equal to the total amount of charge that is passed through the solution. So greater the amount of charge that is passed, greater the amount of material that will be deposited or liberated at a particular electrode. So weight of the substance that is obtained, W, that will be equal to I into T. Know that the total charge that is passed, Q, can be written as a product of current and the time period for which that particular current is passed. So the product of these two will give you the total charge, and said here that is called as the electrochemical equivalent. That is the amount of substance that is deposited for 1 ampere current when it is passed for a period of 1 second. Right? So this is the first law of electrolysis that was proposed by Michael Faraday. Now moving on to the second question, what will be the products that will be obtained during the electrolysis of an aqueous solution of sulfuric acid? So in the case of aqueous solution of sulfuric acid, both sulfuric acid and water will ionize. So sulfuric acid will ionize into the corresponding ions, will get 2H plus ions and SO4 2 minus ions. Similarly, water will be ionizing into H plus and OH minus ions. So we have to see which are the reactions that are going to occur in the anode and cathode. Right? So the cathode reduction reaction will be happening. So we'll have to look at only the cationic species. In this case, we have only H plus. So at the cathode, the H plus that we have, that will be reduced into hydrogen gas. Right? So that will be the reaction that will be happening at the cathode. That means we have H plus, so we'll have 2H plus that will attain 2 electrons and that will be converted into hydrogen gas. So that is the reduction reaction that is going to happen at the cathode. Now the anode oxidation reaction has to happen, but there we have 2 anionic species. We have both SO4 2 minus and OH minus. So if you compare between these two, OH minus will be easily oxidized because that has a lower potential. So OH minus will attain an electron and that will be converted into OH. And 4 hydroxide ions that will react to that to give you 2 water molecules and oxygen gas will be liberated. Right? So the production of oxygen gas, that means oxygen gas will be liberated at the anode and hydrogen gas will be liberated at the cathode. So those are the products of electrolysis of an aqueous solution of sulfuric acid. Hydrogen gas will be liberated at the cathode and oxygen gas will be liberated at the anode. So that answers our first two questions. And the third question, consider the reaction Cr2O7 that is being converted into 2Cr3+. What is the quantity of electricity in coulombs required to reduce 1 mole of dichromate ion, that is K2Cr2O7? So you can see that Cr2O7 2- is being converted into Cr3+, right? And you can see the number of electrons involved here in this reaction is 6 electrons. So the number of electrons involved is 6. So if you want to convert 1 mole of substance and there is only 1 electron involved, the amount of electricity or the amount of charge that is required will be 1 Faraday. So since there are 6 electrons involved in the reaction, the amount of charge that is required will be 6 Faraday. That means 6 Faraday, that will be equal to 6 into 96,500 coulombs of charge will be required for this reaction to happen. So we have been asked the quantity of electricity in coulombs, that will be equal to 6 Farad, that is 6 into 96,500 coulombs of electricity. Right. Now the last question, that's a numerical question. If a current of 0.5 ampere flows through a metallic wire for 2 hours, then how many electrons would flow through the wire? We have to find the number of electrons that would flow through the wire during that particular amount of time. So we have been given the amount of current, that is 0.5 ampere, and for a time period of 2 hours. So if you multiply the current with the time, we will be getting the total charge that has been passed through that wire during that entire time. But we have to find the number of electrons, and for that we now know the total quantity of charge. So if we want to find the number of electrons, we can divide the total charge by the charge of 1 electron, that is 1.6 into 10 raised to minus 19 coulomb. So thereby we can calculate the number of electrons that has been flowing. So first we have to find the total charge, that is Q is equal to current into time. So total charge, that will be the current, that is 0.5 ampere into time. The time here it is given as 2 hours. So we have to convert that into seconds. So that will be 2 hours into 60 minutes into 60 seconds. So that will be equal to 1 by 2 and 2, they will get cancelled. So that will be 36,000 coulombs. So that will be the total charge that we have. 36,000 coulomb is the total charge that has been passing through the system. And now we have to find the number of electrons. For that we can divide this total charge divided by the charge of 1 electron. So that will give you the number of electrons. So the number of electrons will be 36,000 divided by 1.6 into 10 raised to minus 19. That will give you the total number of electrons. So that will be 36,000 divided by 1.6 into 10 raised to 19. Right. So we can write divided by 16, 36,000 into 10 raised to 19. So that will give you 36 divided by 16 into 10 raised to 22 electrons. 10 raised to 22 electrons. So that will be the total number of electrons that will be passing through the wire within the given period of time. Now the final question, 35th question, we have to complete the following chemical equation. There are 3 chemical equations given here. We have to finish the chemical equations. The first equation, we have Cr2O7 2- reacting with the Fe3+ in acidic medium. So what will be the action of dichromate ion with the Fe2+ ion in an acidic medium? So we know that dichromate is a strong oxidizing agent. So that will be oxidizing Fe2+ into the next oxidation stage, that is Fe3+, and the Cr2O7 2- that will be reduced. And the second equation, we have CrO4 2-. We have the chromate ion. What will happen to the chromate ion in acidic medium? So we know that both the chromate ion and dichromate ion that is existing in equilibrium in accordance to the pH of the solution. So in this case, the chromate ion that will be converted into a dichromate ion because the medium here that we have is acidic medium. And similarly, in the last case, that is the ionic equation corresponding to potassium permanganate KMnO4, we have MnO4 minus ion reacting with the oxalate ion. Right? So MnO4 minus here is also an oxidizing agent. So that will be oxidizing the oxalate ion into carbon dioxide, and the species MnO4 minus ion will be reduced. So let us see the complete balanced chemical equations here. The first equation, we have Cr2O7 2 minus Fe2 plus and 14H plus. So you can see that the Fe2 plus ion that is being converted into or oxidized into Fe3 plus, and Cr2O7 2 minus is being reduced into Cr3 plus. So here the oxidation state of chromium is 3 plus. So here the oxidation state of chromium that will be 6 plus. So chromium is being reduced from plus 6 to plus 3 oxidation state, and iron is being oxidized from plus 2 to plus 3 oxidation state. So after you write the balanced equation, we have to check whether the charges are equal on both sides of the reaction. So here we have the total charge. If you consider the LHS of the reaction, the total charge will be 14 into plus 1, that is 14. And owing to 6 Fe2 plus, we will have 12 positive charge. And for Cr2O7, we have 2 minus positive charge. So we will have a total of 24 positive charge that is present in the LHS. So the same 24 positive charge should be present on the RHS of the equation also if the reaction is balanced. So let us check it that. So we have 6 Fe3 plus, we have 18 positive charge, and we have 2 Cr3 plus, so that will be 6. So 18 plus 6, that is equal to 24. Water is a neutral molecule, has no charge. So you can see that the total equation is fully balanced. Now the second equation, as we have already said, depending upon the pH of the solution, there is an equilibrium between the chromate and dichromate ion. So we started with the chromate ion, and since the solution is acidic, it is going to exist in the dichromate form. And in the basic solution, the dichromate ion will be converted back as the chromate ion. So that is our equation. So we can see that in both the cases, if you take the chromate and dichromate ion, the oxidation state of chromium is the same, and see that H plus here is being converted into water. That is the only change that is happening. And the third reaction, the reaction of MnO4 minus, you can see that MnO4 minus here is being reduced into Mn2 plus. You can see C2O4 2 minus, the oxalate ion is being oxidized into carbon dioxide. You can see that the 2 minus oxidation state is being increased to 0 here because carbon dioxide is a neutral molecule. You can see in the case of MnO4 minus, the oxidation state is being reduced to 2 plus oxidation state, and H plus is being oxidized into water. So that is the balanced chemical equation for the three reactions. So all these reactions are in your textbook. These questions has been directly asked from the textbook. Now the B part of this question, the final part of the final question, how is the variability in oxidation states of transition elements different from that of non-transition elements? Illustrate with example. So we have to say what are the differences that we see in the case of transition metals and non-transition elements. So in the case of non-transition elements, we can see they are able to show variable oxidation states, that is due to the presence of their d orbitals, and in that case the metal that can show the most number of oxidation state that will be present in the middle of a series. So if you take the 3D series, you can see that the element that is present in the middle, manganese, that will be able to show all the oxidation states starting from +1 to +7. Right. So you can see that the variation in oxidation state that is observed here, that will be in the difference of 1 unit. So you can show +1, +2, +3 oxidation state. Whereas if you take the non-transition elements, if you take the representative elements or the p block elements, you can see if you take the 15th group element, for example, the most common oxidation state shown by them can either be +3 or it can be +5 oxidation state. And when we move down the group, you can see if you take a heavier element in the 15th group like antimony or bismuth, we can see that the lower oxidation state, +3 oxidation state, is more stable than the +5 oxidation state. That is due to the inert pair effect. You You can see that the s electrons will be reluctant towards bonding. So the lower oxidation state, excluding the s electrons, they will be more preferred as we move down the group in the case of representative or p block elements. But the reverse is true in the case of transition elements. You can see as we move down the group for heavier elements, the higher oxidation state will be more stable in the case of transition elements. So this is how we differentiate the oxidation state, the nature of oxidation states that is observed in the case of transition elements and the remaining elements in the periodic table. So we have answered all the questions in the question paper. Hope all these topics are clear to you, and all the best for your exams.